All right, so that's the other thing about equations and formulas. You look at equations, say like in algebra, and when you first start looking at them, and maybe even now when you look at them, it's just a bunch of letters and numbers with some symbols on a piece of paper, and it doesn't mean anything, right? It's just a jumble of stuff. But what it really is it's a relationship between those numbers and letters. And the formula is a very specific relationship between, you know, certain letters that represent specific things like distance and rate and time or whatever. But that's like if you were to draw like your family tree. I know when you draw your family tree, the parents go at the top and then the line goes down and all the kids, and then if the kids get married and have kids, and it makes this big like tree thing. That's why they call it a tree. And that those lines that connect you are all of your relationships. In math, all of the symbols, the brackets and the fraction bars and the pluses and the minuses and the equal signs are those lines that would connect you in a family. It's just connecting those numbers. And it's explaining how the relationship works. So instead of being a big branching tree where you have to kind of follow the path down and go, okay, this is mom and that's the kid and then that's their kid and then there's those kids and that must make them their uncle or something, you know. You can follow the lines to figure that out. And in math, you follow the symbols to figure out how everything's related. And what makes it confusing is that you have to have a good basis in number theory to just automatically look at those things and see the relationship. Otherwise, you have to work it out. Mathematical modeling is the process of finding the formula. There's a C in that word. Okay, so mathematical modeling. Mathematical modeling is used in business for projections to see, you know, sales projections, production projections. Do we need to hire new people? You know, all these predictions. It's used in the stock market. Stock analysts use mathematical modeling to try to figure out if stocks are going to go up and down. Banks use mathematical modeling to figure out interest rates and loan payments and finance charges and everything. The modeling is probably the most frequently used kind of math because it's used like across the whole board. Like they use it in the medical field and they use it in science and they use it in business and they use it in schools and all over the place. Even like architects and city planners use it because they have to figure out, you know, when they're building roads and things, how much traffic is going to be on there. They have to model that so they know to build the correct infrastructure and put in enough lines for electricity and whatever. And then the actual models are the formulas. Okay, so if I just said 5 5x minus 3y plus 2z equals 77. That's just an equation because that x, y, and z that doesn't mean anything. To actually be a model, x would have to represent one thing, and y would have to represent another thing, and z would have to represent another thing. So maybe like if we're talking about how many power lines we need to put in, x would be the number of houses that are being built, and y would be the number of people that are going to live there, and z would be how many appliances they have or something, you know? Modeling. This is the yearly increase in the average tuition at public four-year colleges. And you'll notice it never goes down. Ever. Never, ever, ever. Just continues to rise. So what we can do is we can create a model based on this data here. Create a formula using this data, and then with that formula we can project out. So like let's say you see this and you have a kid in 2007 and you say, okay, well, I want to start saving for college now. How much is college going to cost in 18 years? Well, you could make the model, use the data here, and project out 18 years to figure out how much money you have to save up by the time they go to college. So we're going to estimate the yearly increase in tuition and fees, and you'll notice like from 362 to 487, and then 725, and then we go into the 4,000. It's not increasing the same amount every single year, right? So what we're going to do is we're going to find the average increase. And to do that, I'm going to take the very last year and the very first year, and I'm going to divide it by the number of years. So that's 8 years, right? 1, 2, 3, 4, 5, 6, 7, 8. Oh, 9 years. Sorry. No, 8. Yeah, 8 years. So I'm going to take that, and it's going to give me 2823 divided by 8. And that is about, and I'm rounding, $353 per year that it goes up. No, that's not exact, because some years it went up less. Like here it only went up about 120. And then some years it went up more. Here it went up 600. So, but on average, it goes up $353 a year. In order to create our mathematical model, we're going to use that. Okay, so we're increasing $353 per year. It goes up, right? So we want to know how much would it be X years after 2000? So we create a model based on the price in 2000. So this is our base, 2000. So that price is $33.62. Yeah, I can't read it. Yeah, $33.62. Okay, so that's our base price. And then if we wanted to know after 1 year, we'd add $353. And then if we wanted to know after 2 years, we'd add 2 353s. And then if we want to know 3 years, we'll add 3 353s, right?
So it'd be easier to just do times, you know, 2 or times 3 or...
Times the number of years, right?
Yeah.
And this will be the tuition. So the tuition will be 3362 plus 353 times however many years that is. Now we want to put this in variables. So I'm going to call tuition capital T. And we'll call the number of years X. So that's our actual model. And that's how we figured out how to write the model. Was we said, okay, we'd start with the 3362, and then we're going to add 353, and then we'll add 2 353s, and then we'll add 353s. And so that helps you to figure out, okay, I need to multiply 353 times the number of years. Does that make sense?
Yeah.
Okay.
So then you're trying to get X back?
Well, no, we could do two things here. If we know the tuition, we could figure out how many years it had been. Or if we know the number of years, we can figure out the tuition. Does that make sense? So we'd have to know either X or T to find out what the other one equaled. But you could do that. That you could say, well, then if I paid blah, blah, blah for college, what year did I go? And you could say, oh, well, let me solve that and figure it out, right? Or if I need to save up for college in 10 years from now, how many years would, or how much would it cost? So let's, yeah. So let's look at 2014. Okay. So our formula X. And we start from 2000. So if we're in 2014, it's been how many years? 14 years. Yeah. Whoops. So 2014 minus 2000 is 14 years. So that's what number I'm going to plug in for X.
Okay, so it'll be
Which is 4942, because you don't have that memorized. Oops. So in 2014, the average yearly cost for college should be, according to this model, $8,304 at a 4-year institution. We could do another one if you guys wanted to. We could use that same model. So let's say let's say somebody has a kid this year, and we're in 2014 right now. Okay, so born in 2014, what year would they go to college on average? Like 18 years later, right? Roughly. Okay, so we're talking 22 years for our X. 32. Thank you. Yeah, good job. I was just seeing if you guys were paying attention. Okay, so the average cost of tuition in what is going on with my pen? I can't go in between these two spots. Do you see that? Like, it won't let me. Okay, I don't know what happened there. Okay, so if you were to have a kid this year and you wanted to save up money for them to go to college, they would need $14,658 per year. Times 4 if they go through and do it quickly, because some people take 5, but if you did times 4, $58,632. Now you've got 18 years to save that up, so we could divide it by 18, and you would have to put away $3,257 per year. Okay, well, if you figure it out per month, it's not too bad. If you break it down that way, now the nice thing about this is if you actually figured this out, right? And we didn't figure out anything about interest or anything, but if you actually put the $270 away per month every month starting now, you'd actually have more than $58,000 because you'd actually collect interest along the way.
Really? Okay.
Yeah.
So I'll put this away.
Yeah. So in 18 years, it would actually be more than $58,000. We'd actually get into in the 60s somewhere. Okay. And here's how a model breakdown occurs. Okay. Models use past data. Okay, I can't use future data to predict the future. I don't have future data. I have past data, right? So models use past data to predict future trends, but sometimes that doesn't work, and so you get what's called a model breakdown. What on earth is going on with this thing? Oh, that's probably really hard to see, isn't it? Sorry. Okay. So the breakdown occurs when the estimate given is no good because the model has been extended too far. Now you guys all know about the housing crash that happened a few years ago, right? So here's what was going on. I'm not going to obviously plot real prices, but before the crash occurred, the housing market was doing this, right? And the price of houses and everything, everybody was happy and it was just going up and they were building and building and building and financing houses and it was great. And then this happened. And the crash happened, right? Well, if I just took data, say, from here, and this time period, so from this year to this year, and then I extended that data out to here, I would think that the money would be way up here somewhere, right? Right. Because I would extend it out too far. And that would be a bad model. Model breakdown would have occurred because actually we're just now starting to do this again, so we're not going to be anywhere near that high. So that's what happens when a breakdown occurs. So you don't want to extend your model too far out from the data that you have. And you never know exactly how far out you can go. And so mathematical modeling gives you a general idea, but it's an estimate, so it's not exact, and this can occur where the reality is here, and then the model goes up still. Questions on that at all? The first part of the process, which is to understand the problem. You want us to write that? Yeah. Okay, so, hey guys. Alright, you want to read the problem at least twice. And I know you guys don't, you're like, I don't want to read the math one twice. But really do. The first time you just read it. Just read it all the way through. And then sort of gives you the general overview of the problem. And then the second time when you read it, you're going to break down the information. You're going to look for the given facts. So any data that they give you, price per pound of something, or how many feet of something, or the numbers that they give you, and then you're going to look for what is it actually asking you to find. And from this, cross out any unneeded information, because that will happen. You'll have a problem that says, in 1987, 2,065 people attended some college or concert or something, and if tickets were $47.50 a piece, and you bought a lot of 50 tickets, how much did you pay? you don't need to know how many people went to the whole concert to find that out, right? So they throw extraneous and random is a way to trick you, because if you're not reading the product carefully, you're going to take that whole 2,000 and multiply it by the $50 tickets or whatever, and then you're going to say, oh, it's this much money, and then you're going to go, I don't know. We only want to know how much your tickets were. So, just cross out any unneeded information. When you read the prompt through the second time, you're looking at the facts, that all the numbers you're given. You're going to look at what is it actually asking you to find, and then get rid of what you don't need. Cross it out. And then it's no longer going to be there to trip you up or confuse you the way they, intended for. Okay. Make a table. Draw a picture. Write a word equation. And what I mean by that is how we were just doing with that tuition modeling, where I wrote tuition equals 3362 plus 353 times the number of years. Because that, you can take that word equation and then put symbols in, and it's easier to kind of put it together that way. Make a table, draw a picture, find a pattern. Use a formula you may already have, like the Pythagorean theorem, or the area of a circle, or volume, or whatever. Make a list of knowns and unknowns and see how they work together. Just things like this. If we're in like algebra, and I want you guys to do distance, rate, time, the two trains leave the station traveling in opposite directions, or those problems that you guys all need. For those, I always say draw a picture. And when I mean draw a picture, I mean like you take this train station, and then you have train 1 going that way, and train 2 is going this way, and then you want to find out how long until they're 540 miles apart, and then you say what speed this one's going. Like, draw the picture, and then it helps you set it up. Because I need to say, okay, there's this distance here and that distance here, and it has to add up to this whole thing right now. So I can take this piece plus this piece equals this. It helps me to set up the problem. Making tables, if you're doing mixture problems, like, I don't know if you remember ever having to do, like, this person is going to take this kind of tea and that kind of tea, and this tea costs $4.50 a pound, and that tea costs $7.95 a pound, and they're going to make a blend that costs $6 a pound. You guys ever remember those? Mixing fruit punch with water to make a different percentage of fruit punch and all that stuff. Those are good with a table. So there's different, techniques that you can use to do this. And that's the next thing. You're just like figure out what's your plan to figure out to solve this problem. Okay. The next step. Oh yeah, I don't know that. Okay. The next step is we're going to carry out the plan and then solve the problem. So after I draw the picture, I'm going to put together the formula, and then from there I'm going to solve for x, and I'm going to find x, and I've got it solved, and then I'm going to look back and check the answer. See if it seems reasonable. If you are solving a problem, like for how fast the guy was riding his bicycle, and you get 278 miles per hour, does that seem reasonable? No. If you're solving a plane speed, like a plane up in the air, and you get like 25 miles per hour, does that seem reasonable? No. If it doesn't seem reasonable, go back and look it over and see, if you're solving for the price of a chicken dinner and you get like $5 million, not reasonable. I don't care where you are, chicken does not cost $5 million. Okay? So check to see if it seems reasonable. And then, just, just sort of look back over your figures. And by obvious mistakes, I mean, on one line, your number was -54, and then when you wrote it down on the next line, you changed it to +54. Those would be the only other things that you would want to do. So if it does not seem reasonable, go back and rework it. And then just look back over your work and look for obvious mistakes. Just make sure that there's not something that's like glaringly standing out at you that like, oh, I was supposed to write down 27 and I wrote down 72. Okay, so just be careful with that. Any questions on that so far? Okay, a man purchased 5 shirts, each for the same discount price. How much did he pay? Right, I cannot understand this. This is not working. Sure, each of the same discount price.
What was the price?
What was that? Yeah, so,
What was the discount? Not enough information.
We have not enough information to solve this problem. We would either need to know the original price of the shirt plus the percentage of the discount to find out what the discount price is and then multiply that times 5. Or we'd have to know what was the discount price.
Mm-hmm.
But we have not, like a man purchased 5 shirts, how much did he pay? 5 times what? I don't have a clue. So, you need to be able to recognize when you don't have enough information. Okay, Alright, a roll of easy white paper towels contains 100 sheets that cost $1.38. A comparable brand, Quick Clean, contains 5 dozen sheets per roll and costs $1.23. If you need 3 rolls of paper towels, which brand is better? Alright, so I read that once through. Okay, easy white, so we'll call it easy, 100 sheets, $1.38. Okay,
5 dozen sheets.
Quick Clean, 5 dozen, 5 times 12, 60 sheets, $1.23. And we need 3 rolls of paper towels. And we want to find out which is the better deal.
Easy.
Easy?
Mm-hmm.
It's only 50 cents more and you get 40.
It's not, yeah, 15 cents more and you get 40 more sheets. But if we want to work that out completely mathematically, you're going to figure out how much does it cost per sheet. The cost per sheet is going to tell me which one is the better deal, no matter how many rolls I need, right? Do you guys agree? So what I don't need to know is that. Whichever one is a better deal, period, whether I buy 3 or 200. It's not like I get a bulk discount. I just, need to know which roll is better. So the price per sheet is we're going to take the price. Okay, so per means to divide. So this is division. So we're going to take the price and we're going to divide it by the number of sheets. And that's how we're going to find out which one is the better deal. So I'm going to do $1.38 divided by 100. And I'm going to do $1.23 divided by 60. Okay. So if I take $1.38 and I divide it by 100, it's going to be 0.0138 per sheet. So penny. And then if I take $1.23 divided by 60, I get 0.0205. So 2 pennies per sheet. So the $1.38 for 100 sheets is the better deal. So that's what we have. Easy, white, paper towels are the better deal. By paying $100 cash up front and $20 a week, how long will it take to pay for a bicycle that costs $680? Okay, so what we have, what information we have is that our down payment
With $100.
is 100, and then our weekly is 20, and our total
It's $680.
is 680, and we want to find the number of weeks.
So can you automatically take out the 100 from the 680?
Yeah, okay, so that's gonna be, hold on, we're gonna come over, no, we're not gonna do that, we're just gonna go to step 2, and we're gonna devise our plan.
Okay.
Okay, you're gonna subtract the deposit,
The total,
and then what?
and then divide by 20. Which should give you your answer.
Which is true. So we're gonna take that $100 down, out, and then it's $20 a week, we're gonna divide by the 20 to find out the total number of payments. So that's our step 3, which is to solve. 580 is left, so we take our 580, and we divide it by 20, and we get 29.
For 29 weeks. What do you mean 29?
Yeah, 29 payments, 29 weeks. Does that make sense, you guys? All right, if you are an engineer and you're programming a toll gate, you know, like where you throw the basket of your coins in the basket, and then the thing comes out and you know. All right, so the gate accepts exact change only, and no pennies. How many combinations must you program the gate to accept? Okay, so we need 50-cent toll, and it doesn't accept pennies, which means it will accept what?
Nickel, dime, quarter, half dollar. Yeah.
And we're trying to find the number of combinations of nickels, dimes, quarters, and half dollars. So like the whole, like how many different combinations of those change could you put together to make
Well, the
it?
half dollar is automatically. 25 combinations.
Yeah.
Oh, you do the same, yeah. Probably more.
Actually, it's less,
It's less.
because this isn't the permutations.
Okay.
But I know you did,
Yeah.
and that's good theory.
It's really not that.
Okay, so
I get it, yeah.
we got 50-cent toll, we've got nickels, dimes, quarters, and half dollars, and we want to find out how many possible combinations of nickel, dimes, quarters, and half dollars will equal 50 cents. Okay, so we're going to devise a plan, and for me, my devised plan is I'm going to make a table. There's my table. I drew that real fast. No. Okay. If I use a half dollar, don't I already equal 50 cents?
Yes.
Okay, so there's none of these, none of those, and none of those. So that's one combination. Okay, now if I don't have a half dollar, and I use 2 quarters,
That's another combination.
that's another combination. Well, what if I'll just get rid of those. What if I only have 1 quarter?
And you would do 2 dimes, 1 nickel.
And if I have 1 quarter, I can do 1 dime and 3 nickels. Or if I only have 1 quarter and I don't have any dimes, I can do 5 nickels. So if I have 1 quarter, I can either have 1 quarter, 2 dimes, and 1 nickel, or I can have 1 quarter, 1 dime, and 3 nickels, or I can have 1 quarter and 5 nickels. So that's 3 single quarter combinations. So far, okay?
Mhm.
Well, let's say I don't have any quarters. How many dimes?
You 5 dimes.
5 dimes and no nickels, or if I only have 4 dimes,
2 nickels.
what if I have 3 dimes?
No.
Right? And if I have 2 dimes, 6 nickels, and if I have 1 dime, 8 nickels, and if I have no dimes, 10 nickels. These are all my combinations. So I have actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible combinations of coins, excluding pennies, that would make 50 cents. Now, if you throw pennies in there, that increases by 1.
Yeah. So that's my combination.
Okay, then we look back over this. Does this seem reasonable? Do you think we accounted for all the possibilities?
Yes.
So we're good. Okay. Oh. Aha, diagrams. Hey guys. Really don't have to say that. Okay, 4 runners are in a 1-mile race. Maria, Aretha, Thelma, and Debbie. Points only go to the first and second place winners. How many different arrangements of first and second place winners are possible? We're going to make a diagram. But first we have 4 people. And they're going to have a first and a second place. And we want to know how many combinations of people coming in first and second. Okay. These I kind of like because this is kind of fun to me. We're going to use a diagram. So we've got Maria, Aretha, Thelma, and Debbie. Any one of those 4 girls could come in first place. So that's what I do first, is I write down their 4 names. And then if Maria comes in first place, any one of these 3 girls could come in second. So you could have Aretha, Thelma, and Debbie. Or if Aretha comes in first, you could have Maria, Thelma, and Debbie. Or if Thelma comes in first, you could have Maria, Athena, Aretha, and Debbie. Or if Debbie comes in first, you could have Maria, Aretha, and Thelma. That's all of your possibilities of first to second places. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Yes, you can take 4 and 3.
Yeah. Now, the other way to do this, if you're talking about combinations where you have things like you know, if you go to Baskin Robbins, 51 flavors?
Yeah.
Is it 51?
Yeah.
31. Okay, 31. And you were going to make 5, you figure out your possible combinations. What you do is you take the number of total available, and you multiply that by the total minus 1. Because once you got rid of the first, like if you can never read, this is only if you can't repeat. So once Maria was first place, she can't also be second place. So we get rid of her. So you do total minus 1, and then if you have another possibility, so for like say 3rd place, you would do the total minus 2, and you multiply that times the total minus 3, and so on and so on, however many spaces you need to take out. 4 girls, guys, seriously. Stop. You have 4 girls total that could come in first place. But once that first row comes in first place, you only get 3 girls that could possibly come in second place. So you can do 4 times 3. And then if you wanted to figure out combinations of first, second, third, then there would only be 2 girls possible to come in third place. So you do 4 times 3 times 2. And then for at that point, this is 1, so it doesn't really matter anymore. Okay? So that's how you can figure out all the possible combinations. So let's do that ice cream. So you said it's 31 flavors? Right? And we want to gonna make a mega cone
A mega cone.
with 5 scoops. With no repeats.
Okay.
So you're not gonna get like 3 chocolates and 2 vanillas, that's 4. You want 5 different flavors of ice cream on your big scoop, right? So my first option would be 31. I have 31 flavors. I pick my first flavor,
Now you have 4.
and now I have 30 flavors to choose from for the second scoop.
Just like my scoops.
Yeah. And then 29 flavors to choose from for the third scoop. And then 28 flavors to choose from for second, third, fourth. And then 27. So if you were going to that 31 flavors ice cream place and you were gonna get 5 scoops, and you didn't want to repeat, and you wanted to figure out how many possible different ice cream cones could you make,
Would it be 31 times 31 is 1?
yeah, 20,389,320 different possible ice cream combinations with 5 scoops from Baskin-Robbins.
That's too many.
This is why, you know those door codes where you have the 5 digits or whatever? There's 9 total digits, but you think, oh, those can't possibly be safe. But you can repeat digits on those. So you actually do 9 times 9 times 9 times 9 times 9, 5 times, which is 9 to the fifth, which gives you, oops,
It's limitless.
it gives you 59,049 possible combinations.
And obviously you can't do them all.
Yeah, somebody can't stand there and punch them all before you come home, you know? So,
That's why I
for
activate
tonight,
those and can actually break those codes.
for tonight on section 1-3, for this weekend, do 1 through 35 odd on sections 1-3. So, page 33 and 34.
Is that what's in the book?
No.
Are we supposed to get a book?
Hold on one second.